Okay, great. So I'll get started now. Hello, everyone. My name is Brian Dieterwater, and today I'll present a metaheuristic genetic algorithm for the multi-depot routing and autonomous bridge inspection. This paper introduces work done by me and Dr. Sushil Lewis in the Evolutionary Computing Systems Lab under the Department of Computer Science at the University of Nevada, Reno.
Recording in progress.
I'll start out by introducing you to the main motivations for improving bridge inspections and how it aligns with the min-max multi-depot Chinese postman problem. For the audience in Singapore, the beautiful bridges around you might be enough motivation alone to further bridge inspection research. I'll then go and discuss 3 prior methods used to produce the solutions for the min-max K Chinese postman problem using evolutionary computing methods. For the method, I'll show specifically how we go from a chromosome representation to heuristics to constructing tours, as well as our bridge benchmark instances used in the experiments. After that, I'll talk about the results where we compare our algorithm against itself with different deployment configurations. Furthermore, I'll show our analysis comparing our GA with the prior genetic algorithm, and some theoretical lower bounds. And finally, I'll wrap this up with our concluding results that the meta GA is 22% faster and 41.72% better than the prior evolutionary computing approach. And I'll leave you with some few unexplored future directions. So, bridges deteriorate and require frequent and costly inspections to avoid catastrophic failures. The picture on the right is a bridge collapse that took place this year in Pittsburgh, the United States. Thankfully, only minor injuries occurred from this collapse, but that's not always the case. Reducing the costs associated with bridge inspections could further prevent events like this. And right now, deteriorating bridge infrastructure accounts for billions per year in inspection costs worldwide. Recent advances in robotics and autonomy can significantly decrease these costs. This is a bridge inspection robot from our colleagues at the Advanced Robotics and Automation Lab at the University of Nevada, Reno. I'll play a short clip for you. As you can see, this multi-directional bicycle robot is highly capable of maneuvering complicated steel truss structures, and it can be equipped with sensors that tell us far more than what the eye can see about the state of steel trusses. Now, the focus of our work in this paper is figuring out how to efficiently route multiple robots across steel truss bridges and what deployment configurations allow for better routes. Following the image in the upper right, we can see we start with a steel truss bridge, in this case a 3D render, and map it to a 2D graph. If we're going to deploy multiple robots on this bridge graph, we'd like to ensure that the combination of robot tours fully covers the entirety of the graph, as you can see by the left center image. Our robot tours should be short, well balanced, with little overlap, and finally we would like the overall inspection time to be reduced as much as possible. Turns out the routing problem that works well for our task is the min-max K Chinese postman problem. The Chinese postman problem is similar to the traveling salesman problem, where our objective is to find the shortest circuit that visits every city, but the difference in the Chinese postman problem is rather than visiting every node, we want to visit every edge. And visiting every edge requires visiting a series of connected edges in a graph. And in the Chinese postman problem and the min-max K Chinese postman problem, we deploy from a central depot, shown as a red star in the center left image. Now, the difference between the Chinese postman problem and the min-max K Chinese postman problem is we have K multiple tours, or in our case, robot routes, where every edge should be inspected by at least one robot. In the min-max K Chinese postman problem, the objective is to minimize the cost of the longest of K tours. Furthermore, we're interested in the deployment of multiple depots. So we focus on the min-max multi-depot K Chinese postman problem for that. As you can see in these images, the only difference is the number of depots. Now we attack the NP-hard min-max multi-depot K Chinese postman problem, MMM-DK-CPP, with a metaheuristic genetic algorithm, meta-GA, to find the near optimal solutions in reasonable time. At a high-level overview of routing problems relevant to this paper, the area that we're focusing on specifically is arc routing problems. And regarding the computational effort required to solve these problems, the CPP problem, one tour, one depot, is easy to solve and can be solved in polynomial time, whereas the MMK CPP and the MMMDK CPP problem are much harder, in fact MP hard, due to the high number of possible combinations and assignments of edges to multiple tours. Here's some prior work that is most relevant. R. and Reinel in 2006 proposed a taboo search algorithm for solving the min-max k Chinese postman problem. In this method, the tours are constructed by splitting and merging subparts of tours, and it also uses some costly repair operators. They also introduced some lower bounds for gauging how far away an objective is from an optimal solution, which I'll show later on. In 2019, Harris and Liu worked on a direct encoded genetic algorithm called DEGA for solving the windy variant of the min-max k Chinese postman problem, which I'll discuss this in more detail in the next slide. And finally, our most recent paper, Routing for Bridge Inspecting Robots Using a Metaheuristic Genetic Algorithm. We introduce a genetic algorithm and focus on the single depot and some more commonly used benchmarks in that. So here's the direct encoded genetic algorithm. The image on the left is an example chromosome where the edge IDs are directly encoded and the actual routes are specified by an R followed by the number. So the length of the chromosome is the number of edges plus k number of tours. So in this chromosome, the first route starts at R1, then edge 1 is traversed, then Dijkstra's is used to connect edge 1 to edge 3 is traversed, so on and so forth, until the sequence is finished for that route. Once we finish reading the entire chromosome, all the routes are returned back to the central depot. This is a good approach because it creates a large search base, which allows for many diverse solutions, as a single tour can have many edge configurations. However, a large search space means that we have to search longer for a good solution. Our approach is a more greedy approach. Here's how we construct tours using the metaheuristic genetic algorithm. In MetaGA, the decoded chromosome represents a set of heuristics to apply to construct tours. So for every value in a chromosome, we select the shortest tour. In the image on the right, this is tour 1. Then we retrieve an edge considering the shortest tour and the heuristic, which I'll go into more detail on the next slide. And then we add the edge to our tour, use cache Dijkstra's shortest path to fix any disconnected gaps to that edge. And if there are no more edges, then we stop reading our chromosome. And finally, we send all our robots back to their deployment points. Here is more detail on constructing an individual tour. So in the first step, indicated by the 1, we read our chromosome and we select heuristic 2. In the second step, we look at our shortest tour, the black line, final vertex, indicated by the green dot, and find all unvisited edges closest vertex and reduce our edge set to only the near equidistant edges. In the third step, we can see that the nearest equidistant edges highlighted in purple, and the blue dot indicates the nearest vertex to the end of our tour. In the fourth step, this is where our chosen heuristic comes in to select an edge. In this case, the heuristic selects the greatest cost edge. And in the fifth step, we add the sequence of edges to that chosen edge. And then the algorithm repeats until there are no more unvisited edges. So researchers have used a standard set of benchmarks for arc routing problems in the past. So in addition to these, we created a bridge trust generator that produced benchmarks used in this paper, which is also available on the GitHub link below. The benchmarks we use are 4 common steel truss types, shown in the right. We have a Howe, a Pratt, a K truss, and a Warren truss. And for each truss type, we have 5 different sizes where we just replicated the pattern along the horizontal axis. For our results, we used the average best objective value found over 30 runs. We compared our 4 depot MetaGA with a single depot MetaGA. and the 4-depot direct encoded genetic algorithm with the CPP lower bound, which is a theoretical lower bound that I'll describe in the next slide. And we also used K values 2, 4, and 8, and we found our results are promising. For the MetaGA, it is 22% faster and 41.72 better than the prior evolutionary computing approach on average. For the genetic algorithm parameters shown in the table, I just wanted to point out our population and number of generations is relatively small compared to DAGA. The direct encoded genetic algorithm uses 1,000 by 1,000, 1,000 population size and 1,000 generations, which explains the speed up that you will see in the next few slides. So before I go into our results summary, I wanted to quickly explain our theoretical lower bounds used to gauge how far we are from an optimal solution. So R and Reinelt described the shortest path lower bound, SPT LB, shown in blue, which is the cost from the depot to the furthest vertex and then back to the depot. We then have the CPP over K lower bound in red, which is the 1 CPP optimal solution divided by K number of tours. And we found the 1D MetaGA follows the combination of these well, as shown by the green line, but it is unfair to compare the 4-depot solution against the shortest path lower bound, since we no longer have a common deployment point. So instead we use the CPP over K lower bound as our theoretical lower bound for comparison. Here is the summarized results for K values 2, 4, 8 with 30 runs best solution averaged results. For each percentage, we show the percent improvement, so values where the percent is greater than 0. 4D MetaGA produced a better objective value than the other value. Each row is for the different truss instance except the last. So you can see of the 20 instances, there are 4 different trusses, 5 of each size. For the columns, column 1 is the truss instance name, column 2 and 3 is the number of edges and vertices, which help give you an idea of the size of the problem. Column 5, 4D DAGA versus 4D Meta. You can see that the 4D Meta shows better improvement on all instances, and this percent improvement increases as the problem size increases. On column 4, the 1D MetaGA versus the 4D MetaGA, we can see overall on all trusses, there's no significant average distance difference, but I wanted to know on all worn trusses, the 4-depot solutions show some improvement, where as the K truss, the Pratt truss instances, the improvement is only on the first truss size. I believe this is due to averaging our different K values, as K equals 8 has a relatively higher objective value on those first few instances. Column 6 is our CPP over K lower bound comparison, where we can see the MetaGA has a worse percentage improvement on all tests, which is fine, since the CPP over K value is not always possible to reach, especially as we divide an increasingly large K value. The most important thing that we can gather from this 6th column is the percent improvement is fairly close with respect to the truss type. Here's a time comparison to reach the best objective value comparing 4-depot DAGA versus the 4-depot MetaGA, averaging the 248 K values per truss instance. We can see here the significant difference in runtime performance per truss instance, and this is where we gathered the 22 times speed improvement. Here we compare the different runtime difference between 4D MetaGA and the 4D DAGA per K value. As the number of edges increases, DAGA exponentially increases in the amount of time to produce good results, while the MetaGA remains linear for each K value. In addition, as we increase the K value, it appears that there's less computational effort required to produce tours. We also wanted to visualize the solutions and see what we can gather from individual routes. Here's the best 1D solution on K-Trust 3, indicated by the red star, and we have 4 individual tours, which are the black lines. We can see that there's no clear patterns between the tours, and if we overlap these tours, we can produce an image like we see in the lower right, where the thick red line indicates more overlap expected near the depot, and the light blue lines indicate less overlap. This is nice to see because we can visualize the full coverage and potential problem areas in our tours. Here's a comparison of different solutions overlap 1 and 4 depots on the instance how to with 8 robots. So in the top image is 4 different solutions, the best solutions resulting overlap from deploying a single depot, and that depot is the lower left corner. And in the bottom row, we can see the bottom image. We can see 4 different solutions resulting overlap from 4 depots being the 4 corners of the graph. In the top row, we can see the overlap is concentrated near the depot, indicated by the thick red line, as expected, since we have a limited number of options for the robots to pick. In the bottom image, we can see that the overlap is less severe and more distributed along the outer edges of the graph. In conclusion, we describe a new metaheuristic GA to the min-max multi-depot K Chinese postman problem that uses 4 simple heuristics. We compare the 4-depot DEGA versus the 4-depot meta-GA and saw an average of 41.72 reduced cost tours for K values 2, 4, and 8, averaged over 30 runs. Regarding the speed, meta-GA reaches the best objective value 22 times faster than DEGA on average, with a linear increase with the size of the instance. We also compared the 1D DEGA versus the 4D meta-GA, or the 1D meta-GA versus the 4D meta-GA, and saw that there's no significant difference on average the results between the 2 deployment configurations. Regarding the visual overlap, we can see, as expected, a more distributed overlap with 4D meta-GA. Comparing 4D meta-GA versus the CPP over K lower bound, we saw that we're not too far off from the lower bound value, and most percentage values were relatively close to each other. We have also provided bridge instance generator and 20 benchmarks and made it all available to access online. Finally, for future work, we hope to look deeper into larger instances, since increasing the size is just a matter of repeating patterns. We'd like to consider ways to include repeating patterns in our algorithm and heuristics. Another thing that we want to explore is more configurations of unvisited edges that the heuristics choose from. So now we're only considering the nearest equidistant edges, but different sets of edges may lead to some further improvement. Regarding the heuristics, we'd like to experiment on some less structured graphs and pinpoint where our heuristics perform well and where they perform bad. Also, we'd like to consider more some new heuristics that allow for better preservations of decoded tours and that better handle a high number of edge options, since our heuristics are fairly simple. Lastly, looking further into differences in our results based on the truss type, we saw that the Warren truss with 4 depots produced better routes than the 1 depot on almost all instances and K configurations, and we'd like to pinpoint exactly why this is. It may have to do with the nature of the graph and the number of odd edges, or odd edge degree vertices, and it could be due to the nature of the algorithm. That is it for my talk. Thank you for listening. If we have time, we can go into some questions.